So the last item on the agenda today is the panel. So let's have the panel speakers down here. So the panel moderator today is Juel. Eric has a PhD from the University of Washington in 1988, and for a long time he was a professor in computer science in the Department of Computer Science at the University of Copenhagen in Denmark. He has also worked with Bell Labs in Ireland, but presently Eric is a professor of computer science here at the Department of Informatics at the University of Oslo. So please, Eric, the panel.
Hello? Okay, you can hear me now. Thank you very much for being here. And we have this panel session now. And you know our speakers, James, and then there's Olaf Uwe, who is a professor here at the department, and Oscar and Ole Lehrmann Madsen from the University of Aarhus, and Dave Thomas, a speaker here. And we'll be talking about Simula and object orientation, and about well, one question posed was, will we still be celebrating Simula 50 years from now when it's 100 years old? Or will it all be forgotten and so on? And this panel, as opposed to many other panels where each panelist gets to give a 10-minute boring talk, I've decided that the format is that we ask questions of the panel, because here's a bunch of brilliant people that know lots of stuff, and instead of them repeating all the brilliant stuff that they've done that we've all read about, it's better to ask them questions and get them to say things that we actually didn't know beforehand. And so I'll start the session actually by asking the panelists, and the panelists should just jump in whenever they want to, and let's just start with the fact, do you think that Simula will still be celebrated? Will we still have a sign 50 years from now that says 100 years? Okay. I guess the answer is no.
Well, I would like to think the answer is yes.
Oscar.
So I have a confession to make. When I was invited to give this talk here, I struggled to think, what should I actually do? And I had an idea that I thought was pretty cool, but I couldn't figure out how to turn it into a 1-hour talk. So my talk was going to be 100 years of Simula. So I would be coming back from the future, and I'm trying to reconstruct the history of object-oriented programming, because this is after the second war with the robots. And I had planned a nice picture of robots. It looks like, yeah, it's a room full of Roombas, 1,000 Roombas. Okay. But the second war with the robots lasted only 2 minutes. We won, thanks to object-oriented programming. But all electronic data was wiped, so all historical records. But object-oriented programming won. I couldn't figure out why, but there had to be some special reason. And what I was doing was coming back from the future to explain this and motivate, and trying to reconstruct the history of object-oriented programming from what few paper records were left. And of course it was going to be completely jumbled and wrong, but I thought it would make a nice story, but I couldn't figure out how to make it last more than 5 minutes. But yes, I think we'll still be celebrating in 50 years.
Yes. And Olaf indicated, and then Ove.
Yes, I think if we were around, it would not last another 50 years. So it's not supposed to last another 50 years.
And Ole?
Well, I actually prepared for this one, even if you said we shouldn't. But as Oscar said, it's very difficult to look 50 years ahead. But I have the privilege of having an old copy, a copy of Christian Nygaard's slides. And in one of them, he referred to, we were at a conference in the 80s with Alan Kay. And Alan Kay has this thing, he says, object orientation is a passing fate. He said that in the 80s. And Kristen Nygaard became very, very upset. He said, this is like saying multiplication is a passing fate. The future is in division. So actually his slides are saying, he refers to Alan Kay, and it's clearly stating that object orientation may become a thing of the past is just as stupid as stating that multiplication may become a thing of the past. But if you go back to this thing about modeling, and I think it seems that we all agree about modeling, and in order to do modeling, you have to be aware about how do you understand and organize knowledge about the real world. And if you look into this, you talk about concepts, phenomena, classification, composition. And I think Kristen managed to convince Alan Kay that this thing about classes and instances, concepts and phenomena might survive and was not a passing fate. So in this sense, I still think we will have something from the old days of Simula on concepts and phenomena. At least it goes back to Aristotle on how you actually organize knowledge about the world. So in that sense, I will bet we are still talking about modeling, but we may not have underlined begin or whatever, end or similar syntax.
And going back to Aristotle, it's like a Plato and the shadows. Thank you. Anyone else want to kick in? Any questions on this? Yes?
What do you think is the best way to get new languages? Rely on the work of some geniuses like Kristen, Oliana, or even Niklas Wirth, or rather huge bureaucracies with competitions? The typical example is Ada.
Yes, I think that in the future, things like reliability and safety will be, information security also will be very important. And that has to be based on some underlying theory, not a committee work.
Ole?
I think if you look at how Simula came into the world, and apparently also Java, it was people working in a specific area with some kind of problems. It will not come from, say, old computer scientists like me that live in a narrow world and has been discussing programming languages forever. You should have some young people, some students that are not just being taught computer science, but are working in a specific application area with some problems that requires something beyond the languages we have by now, and this might drive something new, actually. Computer science is too much being something in itself a little bit too much. So I don't think the new ideas come from there.
As a follow-up, I could ask, Simula as a language in industry is essentially non-existent, not used any longer. Java is quite successful because it was, as James has said, designed by an engineer for engineers, is my impression, right?
And sort of like, so Simula, you know, a lot of what's in Simula was motivated by a task domain, right? It was motivated by simulation, but gee, you know, a bunch of those ideas carry through. And, you know, in a similar vein, Java was motivated by a problem, you know, that, you know, was originally about, you know, doing these distributed Internet of Things that needed security and networking and all of that. And you know, I'm a big believer in sort of design by problem solving. You know, if you don't have a problem to solve, then you don't have a problem to solve. So just like coming up, you know, it's like waking up in the morning and saying, I'm going to invent a programming language.
Right. So it's like I tell my students is that that's an excellent solution in search of a problem.
Yeah, and that's one of the worst phenomena out there.
Yes. And so, Dave?
Customers are constrained, right? Basically, having constraints is good. Because they force you to solve a problem. And so having customers, having a schedule, having to actually get something there causes you to make decisions and constrains your design versus, being in a room where you can just dream about what your language is going to be is very lonely and very egocentric sort of world. So I think I agree. I think the next languages are going to come from different places. If you actually look at Julia, for example, it's physicists who decided they wanted something better than R.
Okay, we have a question from the audience.
It's actually just a follow-up question. By the way, welcome, James. I'm from Oracle. And we are discussing still all the things that you've done and you haven't. Olaf Ove actually began, we were talking about the next generation languages, we started thinking about it. But Olaf Ove began by putting a couple of targets, what we need to be solving, reliability, maybe validation constructs or whatever. I know what he's interested in, what he has been interested in. But that would be a very nice thing to see. You, in a sense, set up the targets of what the next generation languages should be able to solve. It sounds as if it's a bit speculative, but we do know that we need some of the stuff already. We have the parallelism, threads, and God knows what that we just talked about. We have maybe special needs from moving into the cloud. It's not just regular programming. It actually is not programming any longer. It's much more development. I usually don't call it programming. It's a lot of technologies around the programming language. So we know more or less what kinds of things are driving what the customers are asking for today. So could you speculate around those targets, not necessarily the constructs, not the language, but what the languages should be able to solve or address in the near future? Thank you.
Okay.
My first stab was like what I said earlier, namely, how do you build reliable systems? How do you build systems that you can trust? So there are all kinds of domains, like the world of flight avionics, right? People try to, how do you write control software for an airplane that you can sort of go to some agency like the FAA or whatever and say, this will make a plane safer. And the current way of certifying things like that is just hellacious. I mean, there's a whole lot of stuff coming up that's, there's this huge rush of people working on autonomous cars. And as near as I can tell, they're mostly goofballs because they don't think about it correctly. And, especially when people start using machine learning without really understanding that machine learning has nothing to do with the human version of learning. And how do you come to trust that a system is actually going to work? In some domains, you don't much care if if a pop-up advertising thing occasionally puts up the wrong ad, no harm, no foul. If your car, turns left when it should have turned right, then that's a big deal.
Ole?
Follow up on that. I think there's a lot to do in embedded systems. And I think that this is also an example of where the full potential of Simula has not yet been explored. There was a discussion before about task coroutines being part of a language. One advantage of having coroutines in the language directly is that you are then able to program your own schedulers. Especially when you use the version that they invented in Lund with being able to preempt a coroutine, because then you can make your own define your own process classes and others, and you have full control over scheduling. And I think there are not really any object-oriented languages that have been catching this up, except for beta, of course, but that's a minor thing. But I still think in that area when we see people, they are a lot of people, they have to fight with a real-time operating system which really is getting away with it. With built-in coroutines, preemptive coroutines, you can completely control the scheduling of your processes, and you don't need an operating system. So there I still think that Simula has something to offer which has not been fully explored.
Okay.
But then you do not need to invent a new language because it's there already.
But and to follow up a little bit on the question, which is what new languages should be developed, I would like to take James's viewpoint is that, well, what are the new problems that we'll be getting that require new languages? We will get new languages if we have new problems. So is cloud computing, is it IoT, is it the world of IoT plus machine learning, will that cause us to have new languages? Uwe?
In the future, concurrent systems, distributed systems, IoT systems will be very important. And object orientation is very good for that kind of systems. But if you look at the semantics, there are so many possible runs, you cannot test them out very well. And the only way is to have a modular semantics so that you can understand one, say, class by itself, test it by itself, verify it by itself. Then you can do something scalable and have something reliable in the large.
And we have a question here.
So I'd just like to comment as a former student of Olaf, I know that he spent most of his life after Simula just trying to solve the problem of how do we actually get programs that are correct, that work the way. So it's kind of interesting that maybe the two most deeply involved people with languages, you and Olaf, both are now thinking about, or were after inventing the languages, were thinking about this particular problem. How do we get to correct programs?
Yeah, and I don't think it's actually solvable.
No.
Right? It's I think that there's a theorem out there that's probably related to Gödel's theorem that says that you can't solve the problem, but the phrase "solve the problem" means that you're doing like Boolean algebra, right, where it's like true or false. But if you like allow a thin maybe in there, all of a sudden a lot of things become solvable, and then the problem is not so much can you solve it, but can you make the maybe sliver really, really narrow? Yeah.
Narrow in on the problem, yes. That's
yes, Uwe?
Yes, I think Olaf programming is understanding. He would say it a little different because he had a lot of bad programs written by students, I guess, so he couldn't understand anything what they were doing. But if you write the class invariant, have some contracts, then you can start to understand much better. So programs that you can actually verify, that's the programs you can understand. So that was what he was promoting and trying to teach to everyone.
Ole?
Well, it doesn't solve the problem, but I still think that this view on programming as modeling, or to program is to understand, is something that is important here. Because there's a huge difference if you teach the students about programming as modeling or as an incremental language modification mechanism, because then it becomes very, very technical. I've seen students, they don't understand subclassing and virtuals because it's explained to them in a very, very technical fashion. If you teach them that these things are for modeling and representing concept hierarchies in your domain, And then back to this thing, to program is to understand. Then you get a program, then it is a much better way to reflect the thing you works on, and you have a better chance of ending up with a correct program. But of course, it doesn't prove things correct, but it shouldn't be too technical. And one disadvantage of the direction nowadays is that with structured analysis and structured design, we got rid of it when we got Simula and modeling. But with UML and programming today, modeling is one word, and most object-oriented programming language books don't talk about modeling. They are very, very technical. So I think we are diversing again, and we should go back. And I don't know how many teachers are in here, but you should really teach programming as modeling to get in that way.
Yeah. One comment I have on correct programs is that my personal feeling is a little bit like James's, is that you can't do it because if you're going to have a program that's correct, you need a specification. And then you might be able to prove that the program fulfills the specification, but how do you know that the spec is correct? Then you need to prove the spec, which means you need a spec of the spec. And So we have a comment up here from the audience.
Microphone before, so I'm sorry. In a sense, it's a follow-up because that is, I have also been a student of Ole Johan Dahl, and that was exactly what I was thinking when he was up there explaining the verification techniques, and when I was using later actual techniques like VDM and Z and all that stuff. It's like coding your coding, and you never know whether your coding of your coding is correct either, so it has to be coded, and it's impossible, basically. In a sense, it's probably, and this is very speculative, watch out, in a sense, it's probably because we are thinking of verifying a program, a programming language, probably. I am an engineer. I come from system sciences and electronics, basically. And there is one theory that says if you can't solve a problem in one domain, change the domain. That's one way of doing it. So maybe that could be discussed. I don't know, as I said, it's pretty speculative. We could probably discuss which other domains we could jump into instead of trying to verify the programs. That could give us solid verification. I don't know whether you would like to discuss that.
So, James.
Things that I've long been a fan of is you know, because the language, I think, is only part of the puzzle. And one of the pieces that has become very important to me over the last decade or so is the tools, and particularly a lot of the fancy constructions that people do in a number of modern tools for doing refactoring, and these are ones where you can take a program in a simple version of a program and then refactor it to another state, and then because of you believe that the refactoring is correct, then the evolved program is now correct. And in my day-to-day life, I've gotten to where I write code now and then, but mostly what I do is I refactor one program into yet another generation, so that it somehow in there are pieces around the tools. I would like to believe that program verification could be made to work, but I have no idea how to solve the spec problem, and I've been burned by implementing a spec exactly, and then discovering that, oh, the spec was wrong.
So, Oscar had a comment?
I think the focus on I'm not left. There we are. I think that the focus on program verification is rather misguided for a number of reasons. On the one hand, the investment in proving program correct depends on there being a specification. But the fact is that real software systems change over time. So specifications have to change and the code have to change. So that makes this kind of heavyweight. But furthermore, even if you could prove a program correct with respect to specification, That doesn't mean that it will run correctly, because you have to prove that the compiler is correct with respect to the language specification, and that the underlying runtime, operating system, virtual machine, is actually correct with respect to the language semantics, and the hardware is correct too. I mean, this is just hopeless. So instead, maybe that's the wrong problem that we're trying to solve. What we should be solving is, how do we make systems that are robust and reliable and tolerant to failures, even though we know that they are not perfect? I mean, that's what we do in real life as human beings. We know systems aren't perfect, but things function anyway because we have other techniques. That doesn't mean that we shouldn't try and write correct programs, but I think the focus there is probably wrong. We need to look at other ways of making sure that our software systems run reliably, even though we know that they will always contain errors.
Yeah, and I think part of that is, what do you mean by saying that a program is correct? Because in a lot of domains, correct means follows the spec, but really, if correct means doesn't fail, that's a little different, right? And as you said, if you can, write software such that it is robust in the face of failure. So in my previous job, I ended up making this sort of deep assumption that I didn't trust that any of the software was actually correct. And so everything had, try-catch clauses, everywhere. I was expecting a fault to happen from anything, and then figuring out sort of recovery strategies, and then simulating all the, making sure that the recovery strategies worked, and making sure that then if it failed and it recovered, that it at least got to a state where no harm was done. It might not have achieved its goal, but it was not dead.
It sounds like that if you have a big complex spec and you're trying to have something work correctly, then the fallback is a simpler spec, and the fallback from that is an even simpler. I know you were working with robots out in the ocean, and a fallback thing could be, well, surface and never go more than 5 miles an hour.
Yeah.
Or
like we always had at least 3 GPS units.
Right.
So don't expect them to be working all the time.
Dave?
It's really robustness that you want to get. Is this mic on? Okay. I think you're really talking about robustness, and you're really looking at trying to, anticipate failure and figure out how to counter against that. I mean, the OTP framework is a very nice example of something for distributed systems, which has put a lot of thinking into this. I think that's very important. I just want to, and it seems odd, since I spoke about modeling, I might as well talk about verification, since that's something else I've said all sorts of rude things about in the past. But I have to say that the DoD project under Catherine Fisher has done some truly impressive stuff of verifying. They're close to verifying operating system kernels, and they've done the state of technology for verifying small critical sections of code, which I think are part of the sort of infrastructure that we run on. The progress there has been significant. They've done a lot of work with autonomous helicopters and so on, and in terms of taking them from a state of being a complete disaster where a child could take them over, to making them so that multiple red teams couldn't crack into them and so on. So I think there's been a lot of progress in that area, and certainly not something where you can get a lot of people doing it, but for small critical pieces of code, I think there is some really good progress there for those few critical pieces of code. But I think for most people, it's really taking the approach of defensive driving, robustness.
Right. Okay. And the next one was actually Stein, but there's someone very anxious who's taken over the mic.
Since I kind of triggered this discussion about the point was not really to make this just verification, since I mean that was what Olaf was doing for many years. But I came to that conclusion that verification, or kind of, since I've worked for a number of years trying to make a PhD out of verification before I switched. I went down to Stan Jessing instead and worked on network. I kind of was heavily involved in this, and my kind of conclusion was reached when I talked with Tony Hoare on the subway here, and he said to me that well, verification hasn't really proved as much so as valuable as we thought it would be, because I was kind of asking similar questions that I did now, and so I was really talking about tools and not verification. So I mean, how can we improve the tooling, or what can we do to make the program correct, not necessarily prove everything.
I can maybe add that, well, specifications, they give a level of redundancy, which means that you have more than one way of checking that the program is doing what it's supposed to do. And there are, you know, specifications like no information should float in the wrong hands. I mean, if you disagree with that, then yeah, then it could be wrong, but there are certain specifications that you are quite sure this is what I want from my system. And there are ways to do that automatically, like model checking, information flow analysis, that can guarantee these things. There are, of course, other specifications that are more difficult to understand. But simple specifications, like money will not disappear in the system and things like that, I think is very useful.
And now Stein Kodel, one of our Professor Emeritus, is here. We'll have the chance to ask.
Yeah, okay. Can you hear me? Yeah. I think one mechanism in programming language is not fully understood, or maybe gotten exactly right. You are talking about robustness, but exception mechanisms. As you said, you have to put try beginners all around. And is that the best way to do it? Could we do something better, or is even the robustness, should it be built into the language at all, or should it be something else? Or could you say something about that?
So I think it helps tremendously to be in the language. I mean, there are a lot of arguments about this. But I guess, you know, one of my sort of learning experiences, and by that I mean somebody taking a hot poker and shoving it at my eye over and over again, was, you know, if you look at C, there's no mechanism in C for exceptions. So everybody does something different. Most commonly what happens is people use return codes that either show up in global variables, God save us, or as return values, you know, so that the, you know, file open method returns -1 instead of a file descriptor number. And the thing that always disturbed me about that is that people would not check. You know, so that you know, there are all sorts of systems where, you know, people would, you know, open a file, it'd have a constant string for the file name because it's always there, you know, and then, you know, it returns -1. They don't actually check that it's at -1. They don't print an error message. They just carry on. And, you know, there's a part of me that just got so tired of dealing with these stupid bugs from people who would not pay attention to exceptions. And
so that's the case for exceptions.
Yeah, that's fundamentally my case for exceptions. Well, and there's sort of two parts to it, right? You know, one is the, you know, saving people from stupidity, and the other is making sure that all the parts of the language where things go wrong, they go wrong in a way that's captured as an exception, or captured in some way that's clean. So So like in C and C++, if you get a null pointer exception, the universe dies. There's no way to recover from that, right? You get a core dump, and you're just done. And if you're trying to build a truly robust system, you need to be able to say, oh, you know, if a null pointer exception happened in that piece of software, maybe I'll just stop doing that thing. Or same thing with like running over to the end of arrays, which is like the #1 source of security bugs on the internet. You know, when you have buffer overflows, being really rigorous about capturing all of those sources of error in some kind of an exception mechanism. Now, whether or not the exception mechanism in Java is perfect or not, I would totally accept that it's not perfect. But you know, the Wild West of C is much less perfect.
Okay, we have at least 3 people who are, and there's one up here. There's the next one.
My question is for the entire panel. What are your views on the topic of modeling in an object-oriented way versus modeling in a functional way, using functions and algebraic data types, for example? And what do you think of hybrid languages like Scala and F#?
So what's the question? What we think about object-oriented modeling versus functional
There
modeling?
were 2 questions, I think. Yeah.
Yes, what are your views on modeling in an object-oriented way versus modeling in a functional way with functions and algebraic data types, for example?
I really think that your language should support object-oriented modeling as well as functional modeling, because functions are very, very good for certain things, but functional programming in general, if you do the whole thing in a functional program, you miss the whole notion of state and transitions between states. So I think the 2 things can go very well together. Very often we say that methods in a class could often just be functions, because you get some input, you transform the state of the object, and then return a kind of value. You shouldn't necessarily have all these intermediate values in the method. So basically, my ideal language would support functions and higher order functions just as well as classes and objects.
And Ove had a comment too.
Yeah, I would say the same thing. I think both have a role, and objects are more heavyweight, and this functional language is more lightweight. So values I would generate by a functional sublanguage, and like the concurrent objects are for me definitely objects.
Dave?
I'll take the other one, an F# and Scala, just to make everybody irritated. So. I think Scala in particular is a brilliant piece of work on a very hard problem. It started out to be Smalltalk and Haskell into one language, and then switched to being Java, which is a lot harder. And I think it's a brilliant piece of work, but and F# is really kind of would have been better. It started as old camel as far as I'm concerned, but it's also a very interesting piece of work. It's just very hard to put those together in the way they are with the seams, because they leak. And the type system, although it's improving for both of them, is still not sound. So I think, if you're going to use those, the companies I know that use those basically have, trained their programmers in real functional programming and real object-oriented programming first, and kind of decide they do the objects for kind of the infrastructure, and they do functional programming for some of the algorithms and things like that. I think that's a very good way to use it, but when you start putting it in a large group of people where one group doesn't understand, delayed evaluation or, some of the other concepts or object-oriented programming, you can have a lot of people sort of scratching their head trying to figure out what's going on. In some sense, it's the same comment as I had earlier on a DSL. If you really need it, then you really need to support it, but you have to tool properly for it and train properly for it if you're going to be in a mixed paradigm world.
Yes, and the next question, Ole Lehrmann mentioned preemptive coroutines, and we have Professor Boris Magnussen from Lund who actually did it, and he has the next question. Not about that. No, that's fine. But
Is this one on? Yeah, okay.
Happy to see you in the audience.
Yeah, we can talk coroutines another day. I was thinking about the Scandinavian School of Programming and modeling. All of you have been blessing how good this has been, both for your, for programming language development and for your own development. But then we heard Ole said something about that the teaching books were technical and we don't know. There's too little of the conceptual framework in it. So I was thinking, if these concepts, we know that it came from simulation. I mean, that's where the class concept came from and so on. And many of us have experienced the first time, at least the old ones of us, have experienced this method, this way of programming from doing simulation stuff. So maybe we should teach it the same way. So maybe, that would be a good way of if you really want to do modeling, and you can just say, not just say to the student that you should model something, but doing concrete, discrete event models is a very good way of conveying that message. I don't mean that we should perhaps educate many people or being doing simulation models again, but maybe it should be an element in the teaching process. So that would be a good way of. Do you think that would be a good idea?
Ole?
This might be a very good thing to explore, and it reminds me that actually the last project that Christian Nygaard initiated was on learning. It was called Comprehensive Object-Oriented Learning. And his viewpoint on learning was that you should start up with a fairly complex situation and not start learning students from arithmetic expressions, control structures, procedures, and maybe you eventually came to classes. So start up with something complex. And he actually used an example of a restaurant. And he has a lot of strange friends. I don't hope he is here. We had some guy he knew that made a lot of drawings of a restaurant, which was then used as an example for all of this teaching stuff. So the students were supposed to simulate this restaurant. And if you ever have access to that, I don't know where they are, but there are some fantastic drawings on how people came in and out of this restaurant. Unfortunately, he didn't live long enough to complete this thing, but I think it might be worthwhile exploring.
Oscar?
This relates a little bit to the previous question as well. So in my first year programming course, I'm teaching about object-oriented design with Java, and I also do the modeling exercise. But for me, the real point, the modeling is one aspect, but what I really believe, and this is why how I try to motivate it for the students, is that if you do an object-oriented modeling, as opposed to a functional design, then the model can evolve more gracefully over time as you change and add requirements. So what I have is, over a series of lectures, I have the same example, which is a small game, actually a tic-tac-toe game. We start by not torturing ourselves about how to get the design right. We simply start by modeling the domain concepts and then slowly, iteratively building and expanding this over a series of lectures as we see more and more features and also look at inheritance and so on. So I think that's the subtext. Modeling, yes, programming is modeling, but why object-oriented programming, object-oriented modeling? Because it ends up being more robust over time. And as we see the model evolve together with the code, we see that, yeah, it changes over time, but fundamentally, we still have the same domain concepts because it's still the same domain. So the models stay robust over time. This is, I think, one of the most important messages.
I have a question up here.
Hello. Thank you for an awesome panel. My name is Olaf Nielsen. I studied here. I learned Simula. It was great. And while I have you guys here, while we have you guys here, I would like to give you guys a softball question.
I know.
I like the idea about 50 years, maybe turning into 100 years. What kind of qualities or features would each of you expect to see in the next 100-year language that somebody is working on today or might start working on tomorrow?
Any response?
Fast. And I mean fast, and fast to build things. I mean, right now it's still kind of clunky to build things, but also fast to execution, and trying to solve, like both of those at the same time is really hard.
Okay.
Yeah.
Uwe?
Yeah, I think concurrency scheduling will be more advanced, maybe integrating it in the language, and maybe also machine learning will play a role in the future. I don't know exactly how, but I think it will do something.
And I'll contribute myself with saying that with cloud computing, mobile devices, IoT, I think that one of the things that we'll be seeing is the robustness in that in having connections break or not being able to talk is no longer an exception. It's a standard event that you cannot hook up. So I'm actually looking at, well, how do you design languages where it's not an exception, it's the norm that you can't communicate and you have to do something else. And this is sort of like developing, how do we write software where we'll try A, but then if not, then B, if not that, then C. And how can we do we need that in a language, or do we need it somehow or other in another way?
Yeah, that's somewhat related to one of my pet peeves, which is that I hate Booleans. Right? Booleans, are all about a black and white universe. And, they're either true or false. There's, there's all kinds of gray areas, there's maybes, there's I don't know, and they all have different meanings. There's all of the sort of fuzzy logic ones where it's like, well, I'm like about 30% certain.
Yeah.
That may have failed when I was testing this, but I don't know, it's likely. As soon as you start programming around squishy notions of truth, then you can start surviving a lot longer.
Oscar?
Just as a comment, there's actually a word in German for that. Jein. It's a very nice word.
Dave?
No, I think to get robustness and hopefully to get performance, you need to have very simple cores. So I think if we're going to build languages, we need to try and have the core of the language be very, very, very small. That it's always a trade-off to try and get the speed at the same time as the size, because often optimization requires adding a lot more information, but maybe that information can be external and used to optimize some portion of the language as opposed to, or portion of the application as opposed to something that requires the language to be extended in a lot of different ways.
Okay.
I agree that this thing on concurrency, distributed systems, communication is very important for embedded systems, cyber-physical systems, IoT, and whatsoever. And as I said before, I still think that Simula has a potential here, because if you use the Simula concepts, you can build different kinds of concurrency frameworks within your language. You don't have to change the implementation. You can build them within your language, and you can experiment with very many different things, and you can develop the concurrency framework fit for your application area, including scheduling. The other thing I think we need something about is tools And it reminds me about a talk you gave at some dinner speech about 10 things you hate about object-oriented programming. And one thing was that a lot of tools displaying the code, the class hierarchies, etc., but very little looking at the objects. When you talk about modeling, the model in this Scandinavian view is really the program execution. If you go to UML, the model is actually the diagrams, but it's like if you do a model in Lego bricks, you say that the model is a description of how to collect things. It's the car you built. So in object-oriented programming, from a modeling point of view, it's the program execution. It's the process of generating the objects and the interplay between them. And there we really need some tools that helps us understand what goes on at runtime. Current state-of-art of debuggers is too bad for that. It's not good enough for that. So I think this is really an area where we need to see some improvements.
Okay. We have 1, 2, 3, 4 people. The next question is from Arne Maus.
Yeah, first a comment, because people were agreed with me that proving programs basically is impossible. I asked Ole Jondal if he's catching integer overflow when you add. And his proof didn't contain, checks for add. One of the worst errors in programming was the Ariane 5 rocket that added to minus, integer overflow went into minus and it crashed totally, $5 billion or whatever it was. But I have quite another question. There was one feature in Simula I liked, which you haven't got in Java. It's you can have functions as parameters to other functions, function pointers or something like that. You might say you have it with the lambdas, but you don't really, because they are short in line. Why didn't you just take the name of another function as a parameter to another one? I mean, functions aren't all that first class. It's class that's first class in Java.
Yeah, I mean, in Java, everything revolves around classes.
Yeah.
And things you think of as function pointers are really just classes with one method.
Mm-hmm.
I've never felt that you needed more than classes.
So keep it simple.
So like the tricks that people could do with thunks in Simula. I always had a hard time with those.
Okay, I can give you the example because my first commercial program, I got $100 for it. It was making a Qualcomm driver for, I could make a procedure that took any function as input and plot it in an XY system. And it was heavily used at the computing center later on. But it was simple to write because I could take F as an input and any F and plot it. Put out all these minor increments for the Qualcomm plotter. So it was useful for me, at least, for my first commercial program.
Yeah, well, one way to think of lambdas is, when you use the thunking mechanism, right? You end up passing two parameters, right? One which is the F, which is sort of the parameter which the inner guy reaches into, and then that goes into the other thing, which is the actual function that you care about.
Yeah.
And with lambdas, those two things are really one. Namely, it's like the parameter and the body. Mm-hmm. And you can use that pretty much in exactly the same way. People do that all the time, and it works out really, really well. And that specific example of being able to pass a piece of code into a plotting library. I mean, that exact example I've implemented like quite a few times, and it's a real joy with lambdas. Before lambdas, it was really awful.
Yeah.
Well, it wasn't awful. It was awkward because you had to create a class.
Yeah. With a specific name of the function, it had to be called F and things like that. Yeah.
Yeah.
And so the next question is up there. There's a mic arriving very soon.
Yes, thank you. So it has been said here that programming is understanding and learning, and I agree with that very much. But what I see as one of the big problems in my day job, basically, as for developing programs, is that what you have to understand is both the very high-level concepts and the nitty-gritty details. And often it's all the details that make programs go wrong. So you have all kinds of small, seemingly unimportant stuff that the programmer has to think of all the time, while at the same time trying to understand the problem and to make the right program for the right thing, etc. And in Java, you kind of have attacked some of that by having, for instance, a garbage collector and have array bounds checks and something like that, that kind of takes some of the details out. While on the other hand, for instance, in C#, they introduced the async and await, which is a way to try to help you do concurrency in an easier way, but still it introduces a lot of new and exciting ways to blow your foot off, and you have to really know what's going on underneath. So my question is, do you think that the future of languages is to try to hide more of the details for programmers and protect them more, or is it inevitable that you have to really be an expert on both the domain and the programming language at the same time?
So I think that there are cases where both apply. You know, for sort of patterns that recur, you know, and the areas around concurrency are, you know, some of the most vicious ones, because, you know, implementing correct concurrent programs is really hard. And, you know, over the years, a whole pile of really cool concurrency primitives have showed up in the Java libraries. I mean, the work of Doug Lee over the last decade has been just amazing. You know, and so if you're using any of the low-level concurrency primitives, you're probably making a mistake. You know, if you're using anything, any of the higher level abstractions that that Doug Lee implemented, you are almost certainly safe. And where the water gets murky is, you know, where you're sort of outside of the safe zones of places where people have, you know, thought about stuff before, and then you're kind of on your own. And then it's often nice to be able to drill down, but also extremely dangerous. You know, solving concurrency bugs is dicey for everyone.
I think next one was down here. Then that's not this one, but someone was another one up there. Yes. Yep. You were after him. Okay. Fine. So this one first. So.
One per customer.
A mic is coming up soon. We should have a mic down here.
Can you raise your hand? Yes. Okay. So we all agree that the design of program. Yes. Have you finished?
Yeah.
Okay.
Go ahead.
We all agree that the design of programming languages depends strongly upon the applications or the domains that we are addressing. But there is also another factor, namely the machinery on which the computer programs run. And today, for example, we know that there is a large funding for doing research on quantum computing and other innovative computing paradigms. And but we also know that for example, if we get quantum computers, then they will be good at certain problems like factoring large numbers, which will, for example, make asynchronous encryption as we have it today a bit problematic. But we will still have conventional computers. But I thought that perhaps if we in the future get new computing paradigms, perhaps some of the problems that are now today messing up programming languages for conventional computers could be, so to say, filtered out. So to what extent do you think that the development of programming languages in the future will depend upon these new computing paradigms that may appear?
So I'll take a stab at it. I think we're so far off from understanding enough about quantum computing, like, does it work at all? But there are other domains where, it's a really great question. So you've got GPUs today that, it's really easy to find really cheap machines that can do like 2 teraflops. Right, if you buy the NVIDIA TX2 module, costs you about $600 US. It does just slightly under 2 teraflops. But trying to write software that comes close to achieving 2 teraflops on that thing, the way that the programming on beasts like that works is so hideous that there's only a small number of domains where people are able to really, really make them fly. Admittedly, that small number of domains is really valuable, but if I had some spare time, one of the things that would be fun, I've always thought, is how would you do a programming language for a GPU, and it would be just really different.
Maybe.
I have the microphone. So you sort of pointed above my head, that's why. One piece of information related to COOL first, Comprehensive Object-Oriented Learning. I probably was one of the last persons that had the what I should call the luck or mishap of managing Kristen at Norwegian Computing Center. There is no managing Kristen, so that's out of the question. And he was very worried. He probably felt that there was something happening, so he put everything on a CD, and we had it stored at the Norwegian Computing Center. I don't work there any longer, but I believe it still is there, all those drawings and everything, most likely. And this guy probably knows. He was there after I left. Shall I ask the question?
Yeah. I'm currently working at the National Archives in Norway. And we have all the stuff, also the drawings. So if you are interested, talk to Birger, for instance.
That sounds very good, because I have some of the drawings and some of his slides, but I think some of us would really like to get our hands on whatever is available here.
Well, the question, that was just a piece of information. The question is sort of related to that. We've been talking about modeling being programming. And in where I work daily, we have been talking a lot about visual or diagrammatic languages, programming languages, or development languages. We don't like to call it programming all the time, because there's a lot of technology in addition to defining the code that goes into it that we have been discussing. So, and it allows for visual tracing, visual debugging, a good deal of stuff that we've been discussing. And there are, I'm one of the advocates because I used SDL in a relatively large project, in one of the earliest projects called the Earth Station project, almost 40 years ago. And we know that it can work, and it does give a very good, robust system. In a sense, it's not any proof, it's not formal proof, but it's a visual confirmation of certain aspects of the system. So we are looking at visual or diagrammatic modeling languages that execute. Does anybody have any idea whether we are to be moving in that direction? We should be moving in that direction. Is that a future in itself? What do you think?
I'll take a shot. I think visual languages tend to be very good in a domain. So there's LabVIEW. There's lots of data pipeline languages, things like that are very good for those expressing those kinds of problems. I think general purpose visual programming has remained elusive. One is just dealing with scale visually. I work with a person who thinks they've solved this problem, but he's the third person that I've talked to that thinks they solved this problem. But they work quite well in a given domain.
Yes. So I'd like to reiterate what Dave said. I've had a look at a lot of visual languages and worked with them over many years. It seemed like kind of a holy grail, but I don't believe in it as a general paradigm. They're very useful in a specific domain. And I think not just for having an executable language, but also for understanding programs. I had a very, very interesting work by a former PhD student, André Kish, who has worked on moldable tools, what he calls moldable tools. Just to give you an example, most debuggers are the same. They just give you the same kind of views of objects, just very generic. And in certain domains, for example, if you have event-driven programming, that's very painful because the stack view doesn't help you follow the event chains. Another example is in debugging a parser, because again, you have the stack view, but it's completely disconnected from the parsing rules. So what Andre has done, he actually developed some prototypes first, and now he has a moldable debugger, which can be adapted to a domain in a very nice way. So he's able to take this and have customized views so that the debugger is aware of the domain concepts from your domain. So now you have then dedicated operations for navigating while you're debugging respective to the particular domain. In addition, you have nice visualizations, for example, of the parsing rules. So you can say, okay, show me where you are in the parse, what the input stream looks like, which parse rule we have, what's being triggered. And what's super cool about this, that the amount of code needed to adapt the moldable debugger to the domain is relatively small. Debugging is a complicated domain, so there the actual code is a bit larger, but still strikingly small. All this work was done in Smalltalk, in Pharaoh's Smalltalk. And he's developed other moldable tools as well. A moldable inspector, for example, where you can inspect and navigate through objects and then have custom visualizations. The amount of code for individual domains is amazingly small. So you could look at his PhD thesis. There's also prototypes which are available online, and right now what he's working on is a moldable editor, which is very interesting.
My PhD is more or less on the same subject. It's the diagrammatic modeling languages I looked at, and my second master's was related to causal modeling, which is, in a sense, putting the modeling language into a context, which is a bit like, I'd love to do that. I'd like to look at that.
Yeah, very nice.
Thank you.
I agree in this thing on visual languages, but to follow up on sort of debugging, I happen to be at Sun Labs working for the self group while Java changed the world. But I still think that the self system, where you simply look at the objects and you program the objects, and you have a very visual runtime representation of your objects, is a very, very good example of a kind of tool where you get a lot of better understanding of what is actually going on at runtime. So I think that kind of direction might be useful for programming languages, for programming in general. Self has some other problems because it's all this big flat world where you easily get lost, but for debugging I really think that there's something to do.
Oscar?
Related to that, which was related to the point that you mentioned from a previous talk of mine, but the disconnect between the source code and the runtime system. Self and systems that were based on Self's morphic system afterwards are the only ones which I know where you can navigate from the running system, from the morphic widgets, directly to the source code. You can navigate back and forth. This I do not see anywhere else. This is the only situation where you have the direct connection between the meta level and the actual model level. And this is something that's really missing and is needed. It's very frustrating when you're debugging systems to not be able to say, well, where is this object in the code?
Fine, there's a question up there.
My question is for James. Your praise of effective Java. You said that some might think I don't need a book about Java, but I need this one. Why would a designer of a language need a book about that language?
Sorry, I had a hard time.
Regarding your praise of effective Java, you said that some might think that I don't need a book about Java, but I need this one.
Yeah,
why would a designer of a language need a book about that language?
Well, so effective Java wasn't really about Java. It was about programming techniques. And, you know, Josh had a lot of really, really good insights about, you know, ways to think about this, that, and the other thing. That were, you know, some of them were sort of, you know, illuminating contradictions in Java or, you know, corner cases in the type system. But a lot of it was just regular programming advice, you know, and there are a pile of good books like that, like Programming Pearls from John Bentley, which has been around forever. And I sure wish he hadn't like wandered off the map and gone bow and arrow hunting. You know, I still pull out Programming Pearls, you know, and it's not that, you know, I know everything. There's a lot of stuff I know nothing about, and there are a lot that anybody can learn from other people.
Okay. More questions? Question up here.
I just wonder about the never-ending execution. Do we need language for describing and then the universal execution that never ends? The classes, the class descriptions are not yet written. They are written, you are writing them under the way. And some classes then become obsolete. You are not using them anymore. You need a class garbage collector. Are any people thinking about such kind of a complex language construction?
I mean, ones where, I mean, there's sort of the immediate version where classes themselves get garbage collected in a runtime, but the harder part is how do you deal with class evolution, and you know, that's always been really hard. You know, we've taken several stabs at it, and you know, one of the things that's proven really hard about class evolution is that you can evolve a class, but you can't evolve all the users of the class right away. You know, in Java, you know, I put in this deprecated thing because I realized I was making mistakes in APIs. You know, I mean, it literally started because I'm horrible at spelling, right? And I spelled some method names wrong, and I deleted them and spelled them correctly, and people screamed. You know, so. And in the latest Java release, JDK 9, this is the first time we've ever removed deprecated methods. You know, so one can implement all the you know, you can invent all kinds of weird mechanisms to handle class evolution, but you know, when you have trillions of lines of code out there, you know, you don't get to go around and fix it all to deal with the evolution. So you have this really messy problem of, you know, how do you move forward while allowing, while not breaking old stuff. And I don't know a good solution to that other than just working really hard and testing and finding out what people care about, and maybe occasionally breaking people and putting out releases of. I mean, we would literally put out early releases of Java with old things removed and wait to see if anybody screams. And if nobody screams, then it's okay. But it's sort of evolution as a science experiment, which I never felt really happy about. But
Oscar?
One possible solution is that you don't allow anybody to deprecate anything unless they provide an automated transformation tool that will be offered as a quick fix. So yeah, it's deprecating. What do I do? Well, click this button and it'll be fixed.
and we did a lot of that with the NetBeans IDE, and that was actually pretty successful, until IBM came out with Eclipse. And then there became multiple IDEs. So if you come up with one tool that will do these automated fixes, you have to hope that nobody else comes up with a tool that doesn't do those fixes. But you also have to make sure that people actually use the tool, right? And there are some ways in which like when lambdas came out, there was a whole lot of really cool tooling put into NetBeans for doing, recognizing cases that could turn into lambdas, and people would go, "Oh, just magically do this," and it's amazing. In some code, it just scrunches it up. But so many people don't use those tools, and I'm not a good cat herder, and developers are cats, and there are a lot of them.
Okay. Further questions? Marco?
This talk about language evolution brought to my mind an old pet peeve, which is not at all related to object orientation. But I think that reserved words in programming language are a bad idea. When a language evolves, in many cases you will need new reserved words, and this will then break all programs that has used those words as identifiers. There are some good old languages which don't suffer from this problem, at least Algol 60 and PL1.
Well, so can I rant about this one? Because so in some of the Algol flavors, they did one of the things that I really hated, which was putting quotes around reserved words, and boy, did that annoy me. I mean, partly, you're hitting. I mean, it's worse than typing parens in Lisp. But then there were the languages like Fortran. So Fortran doesn't have reserved words. But if you look at the Fortran syntax, I mean, not only does it not have reserved words, but spaces are insignificant. And so the syntax of Fortran is all very strange in some ways that are only explicable because there are no reserved words and they have to be able to parse things. But so I had this really strange experience early on in the Java world, which was in very early versions of Java, there were many fewer reserved words. And in particular, no types were reserved words and no like declaration modifiers were reserved words. So it could tell that something was a modifier just by that, you know, so a declaration was always a place where there was 2 words in a row at least. The last word was always the variable name. The second to the last word was always the type name, and all the ones before that were modifiers. So there were namespaces for modifiers, types, and variables, and they were distinct. And you know, types like, you know, int and boolean weren't reserved words. And things like public and private were not reserved words, and transient was not a reserved word. And one of the reasons that I like that was exactly as you said, you know, you want to be able to later on like add new things like modifiers. And that's the way Java was for you know, quite a long time. And I actually never bothered to document it. It just sort of worked for people. And but at some point, you know, I gave a talk about sort of the syntax of Java to a group of people. And you know, when it sort of came out that public was valid because it could tell that, you know, it's a public variable whose type is public and the name of the variable is public. And it is completely unambiguous. And nobody would actually do that, but the fact that you could do that made an army of people really, really upset. And that was another one of those things where it was like far more than 3 people came after me with baseball bats. And so even though I thought it was the wrong thing to do, I actually made a bunch of them keywords, which I, you know, eventually regretted because we needed to add a whole bunch of modifiers. And then in order to handle the need for modifiers, the @ annotations came in. And it's like every time I type an @, you know, it's like, why did I give in to these people about keywords? So yeah, hindsight.
I'd like to bring the discussion up a little level because we were talking about the programming language aspect of it. What new concepts would I like in a programming language? I would like to be able to write programs which would convince myself that they were probably more correct than in other previous languages. That is, in a sense, what one of the major things Simula gave me from starting, the ability to convince myself that I had understood the problem I was describing, and it was actually a functioning program doing what I expected to do. And so that concept of a language, to be able to describe my problem accurately, to be able to describe the problem accurately in discussion with colleagues, is in a sense, to me, very important part of a programming language.
I agree.
Comments? Over.
Yeah, I think clean semantics is of course really important, and we mentioned earlier concurrency control. So like if you have clean constructs for that, like Simula had detach, you don't destroy any other coroutine by saying detach, you just do something with yourself. Call, detach, resume are very, very good constructs for organizing the coroutines.
Oscar?
I feel that one of the best tools for convincing myself that programs are correct are not so much language issues, but just applying design by contract, letting myself state explicitly my assumptions at various points in time, and that helps me be sure that the program is doing what it's supposed to do. And of course, then programming as a high level of abstraction as possible. I always tell my students, if your method doesn't fit on a screen, then it's way too big.
When we had a question down here, Mike?
Just a short remark. We will never get rid of all the programming mistakes we will make, but I think it's a good sign that the shorter the program, the less errors we have, because the number of errors per 1,000 program lines is more or less a constant. So a Simula program has less errors than a comparable assembly language program. So the more abstract our programming style is, the less errors we will have in the end. Just a short remark to follow up to Markus. As I mentioned already yesterday during the ASU conference, the short ASU conference, it's really a funny story that until now, we are more or less supplying a pile of punch cards to the compiler. In our current environments, it would be very easy to distinguish between an alphabet for variables or identifiers and a separate alphabet for not reserved words but keywords. So just by switching the alphabet and use the ordinary program text only for the interchange of programs. And then it wouldn't matter how ugly the markups were, like apostrophes or single quotes around reserved words. So it's really a funny thing that we are on this very primitive level of programming that we are just simply type in ordinary text lines and supply them to the compiler.
So I want to step in there. Sorry, I keep interrupting and taking over, and I feel like I should just shut up and run away. But you know, there was this earlier discussion about sort of visual tools. And I've always felt that, you know, your point in that they really fit together. You know, the fact that there's this sort of thing about programming that a programming language must be expressible in 7-bit ASCII. You know, and most people actually don't know that these days you can actually use all of Unicode. You know, I write programs that have Greek letters in them in identifiers. You know, if you're doing spherical trig, which I did a lot of in my last job, you know, using Greek letters is really nice, and it's a really small thing, but you know, it makes a big difference. And you know, at various times I've tried experiments of doing like editors that display things very graphically, and never found a thing that worked terribly well. But you know, the thing about a lot of the sort of visual programming things is that you know, people sort of made the comment that they often don't work sort of beyond a certain level of detail. And you know, one of the things that I love about object-oriented programming was like that comment that somebody made that, you know, it's objects all the way down. I think that was that you? That maybe, you know, it's objects all the way down. You know, with object-oriented programming, you can do objects all the way down, and it works really well. But sometimes it's not really the best way to conceptually think of a program. You know, if you've got like a finite state machine, a diagram works a lot better. And you know, so is there a way that you can, you know, pop back and forth and sort of have a language that at one level is text, but there's a way to say, okay, I want to see this as a finite state machine. And, you know, I feel like there's, you know, easily a dozen PhD theses there.
Dave?
Well, you know, Algol 60 had a publication format. You know, I think that's a big omission from a lot of languages, that they don't have a nice way. There's a wonderful book by Marcus and Becker on the typography of programs, was done many years ago, about how you should publish programs with fonts and colors and everything. I really, you know, we don't even have decent pretty printers in many cases for these programming languages. I think if someone designs a programming language, they should come up with a publication format for it as well, like the old Algol 60 had.
Okay, good. we're nearing the end here, and I have a few questions for the panel. One of the things I could ask is, well, what was great about Simula? But on the other hand, I think we all agree that, you know, objects, classes, inheritance, things like that. So what I want to ask is, well, what would you have, you know, what would you have omitted from Simula, or what would you say was a mistake, or where was it went wrong? And several of you have designed programming languages, which means in some sense, Simula wasn't good enough. So why did you know, what were the things you wanted to change and why? So, Dave, you want to start?
Well, I'm not a Simula expert, so I think for me, one of the things that, since we were working in embedded real time, we really needed a model of concurrency that would deal with that. The coroutine model wasn't enough. And I think the other comment that came up, the issue of scope control, I mean, for its time, it was really brilliant, but I think as you get into larger programs, having more control over scope is important.
Okay, yes, and certainly when you say concurrency, I mean, coroutines are not really truly concurrent, they're pseudo-concurrent, so it's definitely...
Well, I mean, I think at the time it was brilliant. I'm just saying for the problems
Work
that
well,
I've come across, it would be.
Ole?
Commenting on a language that's 50 years old is like complaining about people burning wishes.
But yeah, sure. Sure, but you're also designer of a language and you did something different, and why did you...
I would assert that burning witches was a bad idea in the 15th century.
I think the Lund people actually solved that in a very elegant way by adding preemption to coroutines.
I don't agree.
Yeah, but
I think that's a quick hack, but it's not the right long-term solution.
Let's discuss that later tonight.
Well, we have bonfires ready for you outside.
But you know, for Simula, a lot of the problems were actually in the details. When you start to look at things, there are restrictions on subclassing. It has to be in the same block level. A subclass must be at the same block level. If you look at the system concept about prefix blocks, there are some, I forgot about it, limitations here. And also, I think there was something about coroutines. Dahl and Wang really cleaned this up with a bit article in 71, providing a much cleaner version of coroutines. And then nowadays, nobody would never build a new language as an extension to algol. But that was sort of state of art at that time.
Right.
So it's very hard to say what should have been done differently, because it was a huge thing at that time.
Right, but I'm sort of looking at what things endure and what was wouldn't endure. So, Ove?
I know that Ole Johan, he wanted to put in interfaces, but came too late. So that's something he missed in the language.
Okay.
Then one further comment. Dahl and Nygaard actually tried to add a value concept to Simula. Because one of the sort of unsolved things we have in languages is this distinction between values and objects. And in Smalltalk, they decided that a value is just an object. But there's an excellent paper by Dahl and also one by Hoare where they talk about numbers. They are really abstractions you need to represent by data structures. And no programming language has a real good solution to this thing about objects and values. They actually made a proposal, but it was rejected by the big companies who were going to implement this stuff. And my friend Birger actually digged the proposal up from the library. Turned out that they had 2 copies left in the library of this paper on how to do it. And I seen similar one for Java a couple of years ago about how to. It's this thing about embedding objects without overhead. They call it values, and they really tried to do something about it, but they were turned down.
Yes.
Okay. Any other comments on stuff in Simula that?
Yeah, well, so this is not a comment about Simula, but the thing about values, that has been such a tough research area for a long time, because it's easy to make it work if you don't care too much about performance. But if you really want to nail all the performance cases, it becomes just crazy. And I've been kibitzing with this group of folks who I think will end up nailing all the corner cases. And then, you know, they have this hope of getting something that actually nails the corner cases in the next version of Java that sort of folds together a lot of work by a lot of people to get value classes to work.
I think that's the issue we use most of the time on the beta project. And whenever we met with Christian during the last 10 years, he started out by saying we should discuss this value thing.
Yeah.
And then we usually started from scratch again, because we discussed and discussed, but we never came to something that we really thought was a satisfactory solution.
Yeah, I spent like a couple of years of my life trying to figure out value classes, right? And you can, coming up with a 98% solution, yeah, you can do that in a week or two. It's the last, but so back to the original question of yes. Simula.
Going away from this value discussion.
Yeah, so into the discussion that you actually asked about. You know, it's really hard to pick anything, because Simula nailed a lot of things really, really well. And, you know, if I was going to pick, like, if I was forced to pick one thing, it would be the way that, you know, because somebody was arguing with me about this yesterday, and then there was a question earlier about it, but it's just sort of the way that qua lets you violate the contract of the subclass.
Right.
It's like, I'm not sure I like that.
Okay, and we had a question up here. Where's the mic? Where is Mike? Maybe it should be turned on or something like that. Is it okay?
So actually, just a comment. I remembered from Ole Han himself. One thing he really regretted that he did, and he actually at one time he was extremely agitated the way that only Ole Han could be about that. That he had taken these features, particularly one feature from Algol, which was the end comment. That you could have a comment after end with no special character or anything starting that comment, so that you could have end and then some text and then semicolon. And if you then had end else begin something else, and you typed the else the wrong way so that it become esly, for instance, which is really easy to do, then the whole thing would become a comment. And he said, he came at one point, I remember he was really agitated. How could I be so stupid to have this in?
I'm sure you didn't use the version of Algol where you had to put an underscore before each of the keywords.
No, so
that was the gear Algol had that, so there wouldn't be a problem. Marco?
As you spoke about values, so Eiffel has this as expanded classes. Is that familiar to you, or?
It's much easier to work in a language that only has value types.
Okay. More questions here? Otherwise, we're approaching 6 o'clock. Oh, there's another.
I have seen that there are some relationship between programming languages and art and philosophy, like Platon, his concept of the idea and the individual, which maps very well to classes and instances. Also, René Magritte's beautiful picture of a pipe, which says "Ceci n'est pas une pipe." This is not a pipe; it's a picture of a pipe, which is also relates to object orientation. Do you see any relations between software programming languages, modeling languages, and art in the future or today as well?
Well, Christopher Alexander and design patterns, if that's the closest I get to art, but Uwe?
Yeah, if you define a very, very nice semantics for your language, you think of that as art. That's what I would say.
James mentioned programming pearls, they're works of art.
Okay.
I think I work with a very gifted visual person. He has some pretty interesting ideas. They're pretty far out, but I do think that his views of programs are really start approaching the looking of art. And if he can do anything for JavaScript, you know, you can turn JavaScript code into art. That will be really wonderful.
Well, I don't like the term art here for programming, because if you look at art and you look at industrial design on the other side, art is for something for the interpreter to look at and then get his own idea about what this is, whereas design is something that's made for people to use. And a program should not be something that everybody gets his own idea about what it is. So it should be more like industrial design, where you design things like this one that everybody can actually use, and it looks nice at all the time. So this thing of the art of computer programming, this is a wrong thing.
Okay, we still have a few people who want to comment, so quick comments because we're running out of time.
We have had this eminent panel talking about programming languages on the basis of that there are humans that will be programming the computers in the future. Because if we had gone 30, 40 years back and James was sitting there and he was sitting with his assembly language, would he predict that after this there would come high-level languages and he would be speaking about object orientation and such? Because most of the concepts that high-level languages brings is for humans to make it easy to express ourselves. A compiler doesn't need a high-level language to express bits and zeros and ones. So could we think that in 20 years from now that it is irrelevant what kind of high-level languages that we have and what constructs there are, because it doesn't really matter to the programmer, which is not a human anymore? Could that be something? Because we don't care about the typography of semantics of assembly language anymore, or most of us doesn't.
I mean, it's an interesting point because, I mean, assembly language is something that's still there, right? It's, assembly language, if anything, has gotten much more complex than it used to be. And in some sense, that's one of the things that has driven high-level languages, because, or at least high-end optimizers, because it's become essentially impossible for humans to write assembly code. I mean, they can write assembly code, but they're kidding themselves, because you'll never get things like register scheduling correct. So if you did, if your definition of a programming language is something that a human uses to express their intent to a machine, the only way that that's going away is if either humans or machines go away. I guess the first one of those would really upset me.
Okay, and we're running out of time. There's one final comment up here.
Goes back to art and programming language. I always said that if you can't write a nice, there is some kind of aesthetics in writing programs. So if the program is ugly, it's probably wrong.
I think I agree. There was the comments about art, and I certainly see code that I think of as beautiful. And it may not be beautiful in, but what the program does is maybe not art, but how it is expressed can be art.
Okay. And with that, I think we'll thank our panelists for giving their talk here.
We thank our panelists, all the speakers today, and Erik for chairing the panel. So this concludes this part of the program. For those of you who have signed up for the dinner,